This is 6.4.23. We'll now first review linear convolution, and then we'll show you how linear convolution is different to circular convolution. So this is our input. We have a finite sequence input. Only at index 0 and 1 we have value 1. We have also a very simple impulse response that has value 1, 2, 3 at time index 0, 1, 2. Remember that to get our output, we perform linear convolution. This is the equation that will expand what xn star hn means. Simply it is this summation, and the interesting thing of this summation is hn minus k. What is x of k? Well, x of k is only non-zero for these two samples, so this infinite sum reduces to only for k equals to 0 and 1. So since we are only interested in k equals 0 and 1, then we can simply brute force write these two sums. So this is x0 times h of n minus 0, which is hn, x1 times h of n minus 1. So how do we interpret this? Isn't hn the impulse response? It is. So this is a scaled version of the impulse response. What about this guy? This is x1 scaling hn minus 1. So this is the delayed hn by one sample. So actually convolution is nothing but a scaled delayed version of hn sum. Now let us brute force show what is x0 times hn. x0 is 1, so all we are getting is hn, which is sequence 1, 2, 3 with index n equals to 0 here. What about x1 times hn minus 1? x1 is 1, so whatever is output is hn minus 1. What is hn minus 1? A delayed version of hn by one sample. So we shifted 1, 2, 3 right hand side by one sample. We shift 0 into this. Why did we shift 0 into this? Because the original sequence is like this. The values on the left hand side of here are all 0 for our hn. So when we shift 1, 2, 3 on the right hand side, this 0 is shifted into this index 0 here, and therefore this is what we get. Now how do we perform the convolution? Well, this is the plus here, so we are just aligning 0, 1, 2, 3 with this 1, 2, 3, and we are adding. So 1 plus 0 gives you 1, 2 plus 1 gives you 3, 3 plus 2 gives you 5, and this last 3 here. And of course outside this are all zeros because there's no value here. So graphically it looks like this. This is 1, 2, 3 produced by x0 times hn. x1 times hn minus 1 is the same 1, 2, 3 with a 0 here, and now we align to add them up and we get this value hyn. So this is linear convolution. What must we be very careful of is this guy. We are delaying h by k sample, and this is a linear shift. We have seen that DFT will produce circular shifting, and because of circular shifting, things are moving into that n sample and causing these values to be wrong later on. And why would this occur? It occurs because when we use DFT to perform multiplication in the frequency domain to realize convolution, we are not realizing linear convolution. We are realizing circular convolution. So what I'm going to show you is this. We are going to take xk and we are going to take hk, and these are the frequency representation of x and h, and when we multiply them together, we are performing convolution in the frequency domain. And we perform inverse, we are getting this equation here. And the difference between this equation and our previous linear one is exactly only at this point. Our h now is being realized as a circular shifting of n sample, depending on how many samples we are taking the DFT of. Alright, in the next few slides, I'll give you an example of circular shifting for the same example. Thank you.